Good morning and welcome to this morning's staff colloquium. I just want to say to the people in Boulder that I'm just told that you cannot see me, or you will not be able to see our good-looking speaker this morning, Hani Farid, but you will be able to see the slides and you'll be able to hear our voices okay. So we apologize for that in advance. Our speaker today is Hani Farid from Dartmouth College, and he's going to talk about digital forensics. Hani is the David McLaughlin Distinguished Professor of Computer Science at Dartmouth. He's also the director of their new institute there called the Newcomb Institute for Computational Science. He's also a member of the Institute for Security Technology Studies at Dartmouth. Hani got his bachelor's degree at the University of Rochester. He comes from Rochester, New York, in computer science and applied math. Got a master's degree in computer science at the State University of New York in Albany. Went on to get his PhD at the University of Pennsylvania, also in computer science. He then went to MIT for a 2-year postdoc. At MIT, he studied brain and cognitive sciences. He's been at Dartmouth College since 1999. His research interests are pretty broad. Basically, the digital media, but at the crossroads of a number of different kinds of sciences and technologies. Computer science itself, engineering, math, optics, psychology. He's got a broad range of research projects going on at Dartmouth, projects in image analysis, which range anywhere from digital forensics, which you're going to hear about today, to things like the digital reconstruction of ancient Egyptian tombs. So his research obviously takes him everywhere. He's got projects also in computer vision, in human vision, medical imaging, and even computational biology. He's got grants from a whole broad range of agencies, and National Science Foundation, of course, but also Department of Homeland Security, Department of Defense, National Institute of Justice, and the Howard Hughes Medical Institute. Hani has published over about 100, I would say, research papers, reports, and magazine articles. In June of 2008, he wrote a Scientific American article on digital forensics. Maybe some of you have read that article, and some of this will be familiar to you. He's also written 2 very recent book chapters. Just this year, they are being published. Popular press is one of the things that has been really kind to Hani. He's got over 100 things that have come out in the popular press about his research. The New York Times published something. It was called Photos as Weapons. Maybe you'll hear a little bit about that today. CNN ran a piece it was called Iran Doctor's Missile Photo Launch. It just came out recently. Washington Post had something called Great Shots That Never Happened. And a big hit was something called Digital Art Authentication. It was November of last year. It was published in about 50 media outlets, including AAAS, Science Update, The Economist, National Geographic, and like I say, about 50 other things. Hani's research was featured about a year ago, I think, on Nova Science Now, a 13-minute segment on that show. He's still early in his career. He's won several awards. He's got an early career award from the National Science Foundation, a Sloan Fellowship, a Guggenheim Fellowship. We're happy that Hani could come and visit us today. It's his first visit to NIST. He's heard a lot about it, and he's anxious actually to meet a few of you this afternoon. We've got some lab tours set up. So without further ado, let me introduce Hani Farid.
Thanks, Jeff. Thank you. Are we okay on volume? Okay. So thanks for that kind welcome. As Bill says, I have been thinking for the last 10 years or so about this issue of digital forensics and digital authentication. And my lab at Dartmouth has been developing computational and mathematical techniques that can authenticate digital media. And let's just start by giving credit where credit is due. The work that I'll talk about today is that of some outstanding PhD students in my lab, Kimo Johnson, Eric Key, Sue Liu, Aline Popescu, Weihong Wang, and a truly spectacular programmer, Jeff Woodward, who takes everything we think about and makes it real so that law enforcement agencies and media outlets can actually use it on the ground. And so what I want to do today is sort of three things. One, talk about the issue of digital tampering, digital manipulation. Where is it happening? Where is it affecting us? How do we think about it? That's number one. Number two is give you a high-level view of some of the techniques that we have been developing over the last decade for authenticating digital media. And number three is dive into some technical detail for a few of the techniques to give you a flavor for some of the underlying mathematics and computational techniques. So when we talk about digital forensics, we probably have the notion that this is something that is relatively new, relatively modern. It is an artifact of the digital age, an artifact of Photoshop, laptop computers, and digital cameras. But the reality is that for nearly as long as this is my first time that I'm not using LaTeX for my slides, and this is what I get. Okay. So we have this notion that it's something modern, but the fact is, as long as photography has been around, people have been doctoring photographs. So this is the nearly iconic portrait of Abraham Lincoln. It is circa 1860, only a few decades after the introduction of the first permanent photographs. And it turns out that it is a fake. It is actually a composite, as you'll see in this little animation here, of Senator John Calhoun's body and Abraham Lincoln's head. This is 1860. Now, you may ask, and I think that's a legitimate question, is why? Why would they do this? Nobody really knows. I've talked to some historians who say that Lincoln had very bad posture. And they felt that there was no really heroic picture of him, so they created one by splicing his head onto the body of somebody else. Of course, Stalin famously airbrushed people out of photographs that fell out of favor, but he wasn't the only one. Mao did it, Castro did it, Brezhnev did it. All the dictators throughout time altered photographs in order to change history. And so, in fact, when we talk about forensics, it is not something new. It has been around tampering has been around for a long time. Today, however, we live in a very different age where it does not take a highly experienced person a lot of time to manipulate photographs. A few minutes in Photoshop, you can do some pretty remarkable things. And so let's talk about where we are seeing the impact of photo manipulation. The first place you have to look is the media, of course. And what I love about giving talks about digital tampering is every time I give this talk, I get to put a new slide here because there's a new instance of photo tampering in the media. This is one of my favorite ones recently. On the left is the actual Jacques Steinberg, who is a very good reporter for the New York Times. He wrote a piece in the New York Times about how Fox's ratings were going down. And apparently Fox got very upset about this. And they published this photograph of him on their live quote-unquote news program, criticizing Jacques and actually another reporter. And you can see that they did all kinds of very mean things to him. The best part about this story is when some media watchdogs called Fox and said, "Are you guys crazy? What are you doing?" They responded with, "We routinely doctor photographs of people we don't like." Most people in this room will not be surprised to learn that, of course. Okay. So it's easy to criticize Fox, and it's easy to say, well, they're not really quite news, let's face it. But they are not the only ones doing this. Reuters, the Associated Press, the New York Times, the LA Times, Time Magazine, Newsweek Magazine, all of major news organizations have either knowingly or unknowingly published doctored photographs. And as a result, For us, as people who read the news and read newspapers and watch television, it is getting harder and harder to understand what's real and what's not real. And I can tell you with very long conversation with Reuters and the AP, the two big boys in this game, they are very concerned about the lack of trust that the public is starting to have in photographs, and they are starting to think seriously about how they can start to authenticate images to return some trust. You gotta love politics. So Governor Sarah Palin was chosen as the vice presidential nomination. I'd say within 24 hours of that, this photograph started making the rounds. I must have received it in my email box about 100 times. And shortly after it was released, it was determined that it was actually a composite. You can see here Sarah Palin. This is obviously the real person. I think this is just some image that was on Flickr, and somebody just created the composite. This is not new. People in political campaigns, what a shock, are doctoring photographs all the time about either their opponents to paint them in a negative light or their own candidate to paint them in a positive light. What is interesting about this, by the way, because nobody is shocked to hear that a political campaign is less than forthcoming and honest about how they depict their opponent, is there have been studies in the psychology and sociology literature that says, even after I show you this photograph, and I tell you that it is fake, it still affects the way you think about the person. It doesn't actually entirely go away. So I'm going to leave this up for a little while. That joke goes better here than it does over in some of the law enforcement agencies, I have to say. So we're seeing the impact of photo tampering in the media. We're seeing it in politics. We're seeing it in our own back door. Shown on the right here is an original photo of a gel. This was the version of it that was actually published in a scientific journal. And you can see what the author did is they digitally removed an inconvenient band. This is becoming a very serious problem. About a year and a half ago, a stem cell researcher from South Korea, touted as a potential Nobel laureate, had published some extremely influential and important papers in Science talking about stem cell research. It turned out that the cloning he was doing was Photoshop cloning, not scientific cloning. The figures had been manipulated and been altered to doctor the results. The Office of Research Integrity, the investigative branch of the Health and Human Services, now estimates that more than 50% of cases that they investigate have to do with doctored photographs. Mike Rosner, who is the editor-in-chief of Journal of Cell Biology, estimates that more than 20% of accepted manuscripts have figures that have to be remade because they've been inappropriately manipulated. We live in a scientific age where all scientific disciplines are dealing with imaging, whether that is biology or astronomy. Images are becoming the data. And since they are so easy to manipulate and there are, let's face it, massive pressures on scientists to produce results, this is the result of it. This takes a few minutes to do. I can tell you in the last year I've worked on 3 cases of investigations of scientists doctoring photographs. In one case, it was 10 years worth of published papers where almost every single figure in the paper had been manipulated and altered, and this was a cancer researcher. So this is not some esoteric field out there that 5 people in the world care about. These are fields that actually matter. And the scientific community is going to have to get a grip on this very quickly, I think, because it's a major problem. Okay, so we're seeing the issue in media, politics, and science. And in law, which is something that I spend a lot of time thinking about these days, it has gotten incredibly complicated, this intersection of digital media and the law. So let me just talk about one tiny little corner of that to give you a flavor of the complexity of some of the things we are dealing with. In 1996, the Congress passed what was called the CPPA, the Child Pornography Prevention Act, which banned virtual or computer-generated child porn. What was interesting about that ruling was prior to that, child porn was illegal because it involved an actual child. Bad thing, child is harmed, it's illegal. Congress said, we are going to ban virtual, does not involve an actual child, because we find the images offensive. We could spend the next hour talking about whether that's a good idea or not, but let's not. In 2002, the US Supreme Court, under a lawsuit by what's called the Free Speech Coalition, which turns out to be just an umbrella group for the pornography industry, sued. The Supreme Court said that the CPPA violated First Amendment rights and overturned it, or parts of it. So what they effectively did, although I don't think they understood they were doing this, is they said that virtual or computer-generated child porn is legal. It's protected. Okay, so what has happened in the 6 years since that ruling is almost everybody who is now accused of child pornography says it's virtual, it's not real. And the burden of proof now shifts. Prosecution has to now prove that every single image actually depicts a real child. And if you've gone to any of the CG movies recently, you know that CG technology is very, very good. And so now courtrooms are struggling, juries, judges, lawyers are struggling with how to deal with this ruling. Now take this one little tiny problem that we're facing and expand it out where you have audio surveillance, video surveillance, image surveillance, digital documents, any type of digital media being introduced into a court of law as evidence is now suspect. And I can tell you both sides of the aisle are raising the specter of how do you believe what you see? And it is a major collision of technology and law because the law is still in the dark ages and the technology has ramped up so quickly that we don't know how to deal with it. It is happening at the national security level. Bill mentioned this. A few months ago, Iran released this photograph here showing 4, I believe they were mid or long-range missiles that had the ability to reach its neighbors. Almost every single major news outlet in the world published this photograph and renewed discussions about whether military action should be taken against Iran because of that photograph. You can see something that's a little funny here. This plume of smoke and this plume of smoke seem to be suspiciously similar. In fact, this photograph was taken by another reporter around the same time and was released, so it appeared that only 3 of the 4 missiles launched, not 4. Now, what's interesting about this is people were not freaked out by the fact that 3 missiles that could reach neighbors were launched. They were freaked out that Iran knew how to use Photoshop. I found that puzzling, but it did raise some interesting questions. If they could have doctored 1 missile, why couldn't they have doctored 4 missiles? Why couldn't, for example, a country who wants to invade another country simply create photographs showing a threat when the threat doesn't actually exist? And so what came out of this was not, oh, it's not really a problem, they can only do 3 or 4. It was, how do we now think about these photographs, video, and audio recordings coming out of various parts of the world when we know they can be manipulated and altered? And suddenly, we were talking about serious geopolitical implications around the ability of a few people to use Photoshop. And that, I think, is an interesting and something relatively new that we're seeing happen. The headline here, I think, is something like, "You thought you were having a bad day." So in general, not only are we seeing the impact of digital tampering in nearly every corner of our lives, we are, as people who spend a lot of time online, starting to not trust what we see, what we hear. And that, I think, is sort of a really interesting aspect of photography. I started off by saying that this is not something new. We've been altering photographs forever. But something has happened in the last 10 years that is new, which is that there is a remarkable amount of skepticism about the things we see. Every day, I get dozens of emails from people all over the world saying, is this real or not? And in the vast majority of cases, it is. But there's this now specter of doubt about everything we see. And that's just, it's not just about sort of, can we trust, but it's impacting us in the law, it's impacting the media, and I think it's changing our relationship with photography and with images and with video. And so we started thinking about in my lab at Dartmouth how you can start authenticating digital media. And I'll spend most of the time, in fact, all my time talking about images, and at the end I'll tell you about some work we're doing in other types of digital media. So here's the philosophy. One way to think about authentication is with digital watermarking or digital signatures. You have a trusted device that either extracts or inserts some type of signature, the way currency is watermarked, and you use that for authentication. A very reasonable scientific mathematical approach, but requires that you have that secure device. And I can tell you in all the cases I've worked on over all the years, you don't usually have that luxury. You are typically simply given something. Often it's something that was taken 5 years ago, things that are coming out of various parts of the country. You don't have that ability. And so we started thinking about what we call passive or blind techniques of authentication. And the general philosophy is to spend an awful lot of time in Photoshop thinking about how you manipulate images, what type of mathematical or statistical property does that disturb, And then how can you detect that? So it's going to be essentially a collection of tools, of forensic analysis tools, each of which can detect a specific form of tampering. And what I'm going to start off is just giving you a high-level view of a few of those techniques to give you a flavor, and then we'll dive into some technical detail on a few of the techniques. Okay. So here's an original photograph, and here's a doctored version. So a very popular thing to do on the internet, the big cat, the big rabbit, the big squirrel. Everybody wants to make big, big animals. The big hogzilla, that was one of my favorite ones. And what have I done here? Well, I've taken a part of the image and I've stretched it. Okay? So let's just sort of think of a toy example of this. So underneath the image, of course, are a bunch of pixels. Each pixel has a corresponding number, which corresponds to the underlying value. And let's ignore the fact that there's color. So let's just imagine this is a black and white image. Every pixel, typically something between 0 and 255, black to white, corresponds to lightness. Okay, so here's a little 3x3 patch of the image, and the underlying pixel values are what I show you here. So what have I done to stretch it? I've taken that little 3x3 patch, and I've made it taller. So I've turned it into a little 5x3 patch. Okay, I only have 9 pixel values, but I need 15. So what do? Well, in this simple example, you take the existing rows of pixels, and you put them into every other row. And now you have holes, and you have to fill the holes in. The way you fill them in is you interpolate. So for example, the 4 is a linear combination of the 3 and 5. The 2 is a linear combination of 1 and 3. Pick your favorite interpolation algorithm. I don't care what it is. It's typically going to be something that's some combination of your neighbors, whether it's bicubic, nearest neighbor, linear, whatever. So as a result, there's a subset of the pixels in the image that have been entirely generated by an interpolation algorithm. So a subset of the pixels are going to be perfectly correlated to its neighbors. And so we've developed an algorithm that can not only find those in only a part of the image, but tell you what the correlations are. So what we seek is a subset of pixels that are correlated to their neighbors in a way that does not happen naturally statistically. And so this algorithm can actually determine whether something's been upsampled. And interestingly enough, you can show mathematically that upsampling and downsampling, rotating, shearing, all do the same thing. It's not just this simple case. Any type of interpolation that moves you off of the integer lattice leaves holes. The holes have to be interpolated, and we can detect those. Okay. The second technique exploits some interesting properties of most cameras. In fact, all cameras but one, which is the foveon camera. This won't work for. So a color image, of course, has 3 color bands, a red band, a green band, and a blue band. That's what gives you color. So you have RGB. So you would think, therefore, that there'd be 3 sensors at the back of the camera, but there's not. There's actually only one sensor for a variety of reasons, everything from economics to signal-to-noise ratio. So you have one sensor that is responsible for measuring at every pixel red, green, and blue. It's not going to happen, except for the foveon camera. So what they do instead is they have a color filter array. So this little picture here represents a very crude camera. It is a 6x6 pixels, so a 36 pixel camera. Obviously, the 6 megapixel has 3,000 by 2,000 of these. And over every pixel is a color filter, either a red filter, a green filter, or a blue filter. And that means that that pixel records how much red light is coming in, that one records how much green light, how much blue, and so on and so forth. So what you have is actually only 1/3 of all the pixels that you actually need to represent a full-blown RGB 3-channel color image. So what do? Well, you interpolate. So in this panel, I'm showing you the red pixels, and the high saturated are the ones you actually recorded, and these are the ones you have to fill in. And every camera does this. They fill in. And the basic idea is they do linear interpolation for most of the image, and near the edges, they do something a little bit smarter to deal with the blurring effect. Okay. So as a result, though, is that a full subset, a significant number of pixels were never recorded. They were generated by the camera. And that leaves a very, very specific signature behind in the image. And so when, for example, you introduce something into the image, you are very likely to destroy those color filter array artifacts. We can quantify that, and we can now detect that. So we can simultaneously figure out what the interpolation is without knowing a priori, and we can tell whether parts of the image are consistent with that or not consistent with that. So in some ways, the sensor has an inherent digital signature built right into it, and we can exploit that. Okay. So what I'm showing you here is magnified view of this part of the image right here. And what you should be able to see is some pretty significant color artifacts. So there's a green band, a magenta band, and a green band here. This is actually a highly exaggerated version of an effect that actually happens in images, which is chromatic aberrations or color aberrations. So what happens is when white light comes into a lens, it bends, and it bends proportional to wavelength or color, Snell's law. And so what that means is that at the sensor level, if you have a white light coming in, there's a slight misalignment between the red channel, the green channel, and the blue channel. And you can take Snell's law and do a first-order approximation, and you can show that it is basically an expansion pattern. That is, that the color channels are misaligned by an expansion or a contraction relative to one another. Near the center of the image, there's almost no distortion because the light is passing right through the lens. Near the edges, the light has to bend more, therefore the aberration is larger. This is why you typically see chromatic aberrations near the periphery of the image. So this little vector field tells you here how much misalignment there is between the red and the green channel. Okay? So what's interesting about that is that there are distortions in the image that are a fundamental property of physics. And so, for example, if I took this fish, which was originally recorded, let's say, in this part of the image, on the left here, and I copied and pasted it to this part of the image, look at its chromatic aberrations. It's doing this. Oh, people in Colorado can't see that. Okay, up and to the right, right? Whereas the rest of the distortions are going towards the center. So we've developed a technique that can measure both global and local aberrations and look for the case when something is moving, well, in this case, almost orthogonal to the direction that it should be moving in. So these chromatic aberrations are very nice. I've drawn them here in an exaggerated way. In most cases, they are a pixel, pixel and a half, or 2 pixels, so it's a very fine-grained measurement you have to make. Only works for high-resolution images, not for low-resolution images, where it all basically goes away. I'm embarrassed to say that I don't read journals anymore, but I do read Star magazine quite a bit now. And the reason is I get a lot more ideas from Star magazine than I do from the IEEE journal. I remember the first time I went to buy Star magazine. I live in a small town in Hanover, New Hampshire, and everybody knows you there, and they keep track of what you're buying usually, too, it seems. And so I got the Star magazine, and the checkout counter lady looked at me, she's like, "What's wrong with you?" I said, "It's for research, don't worry." So this is one of my favorite covers. It shows Brad Pitt and Angelina Jolie when they were still rumored to have a relationship. And what I love about this is when you first look at it, you've got 2 beautiful people walking down the beach, everything's fine. So let's look more carefully at the lighting in here. So it's obviously outdoors, sunny day. You have a cast shadow of Angelina Jolie on the beach. Her face is largely equally illuminated, and you have a drop shadow under her chin. So all suggestions are that the sun is somewhere over here to her left and up, which is causing the drop shadow. Okay, if the sun is over here for her, let's look at Brad. You see it? Where's his sun? I think they may have their own sun that follows them around, so it's not impossible. This is a good 120 degrees wrong. I mean, it's really unbelievably broken. And what's amazing about this, and I do this for a living, is when I first looked at it, I didn't notice. It was only after the cognitive exercise. And I contacted some of my colleagues who do human perception, and they told me that there's been studies that say your brain doesn't care about physics, and I'm really sorry about that, Bill. Basically, inconsistencies in things like lighting, shadows, and basic physics, your brain simply ignores. It doesn't actually care about it. And it can be really wrong. And it doesn't have that pop-out effect, like something's wrong with this thing. Now, obviously here, we could do the cognitive exercise and see that something is very wrong. But we started thinking about, well, what if it was just 10 degrees or 20 degrees? That's going to be very, very hard to see perceptually. So now let me dive into a little bit of technical detail of how, from an image, you can determine where is the dominant light source that is illuminating. Because that's a very, very hard thing to undo because it is the result of 3D effect. The light is in a 3D position, you have a 3D object, all the shadows, the gradients, everything is an artifact of that, so fixing that in Photoshop is actually a little tricky. Okay. So let's start with a simple assumptions, okay? And I'm gonna pull back on all the assumptions in a little bit. So I'm gonna assume I have a very simple object that is a uniform color and is Lambertian, which simply means it's sort of like a matte surface, it's not specular. And I'm going to assume that I have a single light source that is infinitely far away, and it's a point light source. So a really, really tiny sun that's infinitely far away. Okay. Under those very simplifying assumptions, which again we'll be able to pull back on, you can write a very simple model for how much light hits the object. Okay? And that model goes something like this. The intensity at that point right there, where you have the surface normal n and the light direction L, is equal to R, which is the reflectance of the object, how much light it absorbs and how much it transmits, an inner product or a dot product between the surface normal and the light direction, and a scalar ambient term, just how much light is just sort of coming around from all directions. Okay? Here's the interesting part, this dot product. So what is this saying? If we assume that n and L are unit vectors, then what we are saying is that the amount of light that strikes the surface is proportional to the cosine of the angle between them. Okay, cosine starts off at 1, goes down to 0. So what that means is that when L and N are in line with each other, that's the brightest part of the object, and the amount of light falls off with the cosine. And you can see that here. Here's the hot spot, which is roughly in the direction of the light, and it falls off with the cosine. And it's not black here because there's an ambient term that's illuminating everybody equally. Okay, so let me just break this out a little bit. N is a 3-vector. It's the surface normal, nx, ny, and z. L is a 3-vector, lx, ly, lz. And A is the ambient term, just a scalar. Okay? We're seeking to estimate what's in blue. We hopefully will make the measurements of what's in red. Now, this is really problematic, R, because there's no way that you're going to figure out what the reflectance properties of things in the world are. So, but it turns out we can ignore it, because we don't care about the scale of this vector. We simply care about which direction is it pointing in. So what we're going to do is we're going to estimate a unit vector, L, which points in the direction of the light, and that means I can get rid of the scale factor and write this as a proportionality. Okay, here's the good news. We have a linear system. This is, if you have known surface normals, you have 4 unknowns, the 3 components of the light direction, the ambient term, and it is linear, so that means it lends itself to a simple closed-form analytic solution. That's the good news. The bad news is we need 3D surface normals, nx, ny, and z. And if I give you this image, unless you know that that's a sphere, you don't have 3D surface normals. You only have, well, you don't have anything actually right now. Now, obviously, if you had more images, or if you had a bunch of Lambertian spheres scattered around the world, which, let's face it, would make our life a lot easier, you're in a little bit of trouble. Okay, so let me talk about some work by Nilius and Eklund, which is very clever, from 2001. These two guys just made a very simple and very clever observation that we're going to take and sort of build on. So let me spend a few slides on their work, and then I'll come back to what we've done. So the whole problem here is 3D surface normals. How do you get 3D surface normals from a flat 2D image? Well, imagine that this is your object here, a sphere, and imagine that the z-axis of the object is coming straight out of the screen, okay? And the x and y are up and down and to the left. All right, well, if that's the z-axis, then if I think about just the occluding boundary here, the z component of the surface normal is 0, right? Okay, so now let's think about the intensity along the occluding boundary in terms of the previous slide. Well, if nz is 0, then I don't care, the influence of lz is irrelevant. Okay? So the good news is I can make this 2D measurement. It's just local gradients on a curve. The bad news is I can only estimate 2 components of the light source direction, Lx, Ly. So what that means is I can tell you that the light is here, but I have a degree of ambiguity, right? The z component in and out of the screen. Okay? So from a forensic point of view, that's actually not bad. And then what I'm going to do is show you later how we can actually get the z component out. We can actually get that nz under certain conditions, or lz rather. But let's start here. Okay, so again, the good news is, now there's 2 good news. Still linear, and we can make the measurements that we need, the variables that are in red. So how do you do this? You walk around your object, the occluding boundary of an object, and you make measurements of local surface normals. That's nx, x1, y1, so it's that position in the image, ny. So here's my unknowns. So this is nx, lx, plus ny, ly, plus a should equal the intensity at that point. Okay, so this is just rewriting in matrix form the previous equation. So now I have a simple least squares problem. I have a matrix of known quantities. I have a vector of unknown quantities. I have a vector of known measurements. I set up a quadratic error function, differentiate, set equal to 0, solve, least squares solution, right? Very easy to do, closed form, analytic, and is the best least square solution. Okay? Again, this is the work of Nilius and Eklund from '01. This is the observation they made. And it works surprisingly well, actually. I mean, really surprisingly well. But it relies on the fact that for all of these surface normals, the color of the object is exactly the same. And that's one of the tricky parts. That's where it falls apart in a forensic setting. So what we're going to do, this is the work of Kimo Johnson's PhD dissertation, is we're going to try to relax that assumption, and we're also, I'm not going to talk about it, but we also relaxed the assumption that the light had to be infinitely far away and that there was only one light source. I'll only talk about one of those relaxations. The rest you can find in a paper on my webpage. So what Nilius and Eklund did, and which I love, I think it's a very clever paper, is they assumed that you had an object with a reflectance that was the same everywhere. Okay? So this guy and this guy had the same color. What we're going to do is we're going to replace that global assumption of constant reflectance with a local assumption. Okay? So what I'm going to do is assume over this little green patch here that the reflectance is constant, but that it could be different from the reflectance over here. So notice what I've done here. I've got L1, which is my direction to my light source, and I've got L2, which is the direction to the light source. They're pointed in the same direction, but notice that this one's a little bit shorter. Why is it shorter? Remember that the reflectance affects the scale or the magnitude of the vector you're estimating, but not the direction. So as the reflectance change, the scale of this thing changes, but not the direction, because we're still assuming an infinite light source. Okay? So what we want to do is take what they did and extend it to this assumption. In the simplest possible form, this is how you do it. It is not a good idea, but it's the first thing to try. You take those little green patches and make a bunch of measurements of surface normals. That's this block up here. And that corresponds to the first light direction. Make another group of measurements in another green patch. That corresponds to its direction. And then you have the ambient term. So it's basically taking their version and just doing a block diagonal matrix and making a bunch of independent measurements along the round. Why is this a bad idea? Well, for a couple of reasons. First is I'm treating these measurements as independent. I'm assuming that all the light directions just are independent, and they're not. We know that they're all faced in the same direction. The other problem is that the patches have to be relatively local, which means that this little block diagonal matrix is almost rank deficient. So the conditioning of it is actually very bad. So the whole system actually turns out to be numerically not very stable. So what you can do is the following. You can take that basic construct that I just showed you, mv minus b squared, and add a regularization or a smoothness constraint. What we're going to say is, typically, unless you're looking at a zebra, the colors don't change radically from space to space. They change relatively slowly. So what we're going to do is we're going to condition the individual light source measurements that they have to be, they're going to penalize big differences in the light direction. Okay? So we take our normal least square solution, we add a regularization term. The good thing is this stays linear. The whole system stays linear, and you can solve, as I showed here, where this plus is a pseudo-inverse. Okay? So all we've did is said, look, we're going to make a bunch of local measurements. We're going to say that the reflectance changes slowly across the contour, and the whole thing stays linear, closed form solution. And I said earlier, you can also relax the fact that there's only a single light source, and they actually don't have to be infinitely far away. So there's 3 things we did to extend it. So when Kibo and I were working on this, we did a whole bunch of simulations, got everything working, and we're ready now to do some experiments. And the obvious thing was to go outside and do some experiments because we had a pretty well-behaved light source. And I started thinking about how we're going to get ground truth out there. And I come up with this I thought it was really clever, but it turned out it wasn't, idea of getting a GPS-enabled camera and figuring out where the camera was and where the sun was and doing very highly calibrated experiments. And I told this to Kimo, and I think his eyes glazed over, because at that point he was only a year away from graduating, and he saw that schedule slipping a little bit. And he said, well, let me think about it. And he came back, this is a true story, 20 minutes later, and in his hand was a piece of cardboard and a stick. And he said, I have a better idea. And as soon as I saw it, I'm like, oh, yeah, I think he does too. So he made a sundial. Clever Kimo. And so this is a little sundial, the stick here, and for full disclosure, this image has been manipulated. We enhanced the shadow because it's a little hard to see. We didn't change the direction, we just made it a little bit darker so you can see it. So the cast shadow gives you the direction to the light source. This is NIST, so I'm loath to say that this is, a real measurement. This is within a couple of degrees, almost certainly, the measurement here. Okay, so these little black patches are the patches that we're making the measurements over. The whites are the individual light direction measurements, and the blue is the vector average of those. And in this case, the actual is, this decimal point shouldn't be here, by the way. It should be 34 degrees, and the estimated is 32, so within about 2 degrees. This is one of the better cases. This is the worst case. We had the parking meters. We are off by about 12 degrees or so. There's 2 reasons for that. One is this is not a Lambertian surface. It's actually fairly specular, which violates our assumption. And these surface normals over here are almost orthogonal to the light direction, which causes a little bit of instability in the measurements. But worst case scenario, we're 12. In experiments we did, both in simulation and out in the world, we're typically within about 8 degrees or so. That's the average error. So within about 8 degrees, you can get 2D light direction. Well, by the way, much better than what the human visual system can do. You can't see 8 degrees. You can see 120 degrees, but you can't see 8 degrees. Okay. So, out on the beach, outdoors, it makes sense to ask, where is the light? But in a room like this, or most indoor settings, it doesn't actually make sense to say, what is the direction to the light source? That question doesn't really make a lot of sense, because the lighting is obviously far more complicated. I got a couple hundred lights in here. There's inner reflections. There's things bouncing off green surfaces and the wood here, and the lighting is very, very complex. And so we started thinking, and this is also the work of Kimo Johnson, thinking about how you could capture or measure more complicated lighting environments other than just where is the light. So let's think about the problem like this. Imagine you have a surface. That's this thing right here, and you have a little patch denoted as x, and the surface normal at that planar patch is n. Okay, so we have the pointing up. And imagine I drop a hemisphere around that patch, okay? And I just shoot rays out in every direction, just sample the sphere, the hemisphere, in every direction, and ask how much light is coming in, how much light is coming in, how much light is coming in. What I have as a result is a function on a sphere, or a hemisphere, right? Telling me how much light is incident for this little patch right here. Okay? So if you think about that, we now have a function on a sphere, and we actually know how to think about functions on spheres. We have very nice tools from spherical harmonics for doing that. So in the computer graphics community, and in particular Ramamurthy and Hanrahan in 2001, showed that if you think about complex lighting as functions on a sphere, you can model them with the spherical harmonics. So these are basically the Fourier basis on a sphere instead of on a line or on a plane. So you can see that. This is the DC term. That's the constant ambient term. These are the first order terms. So these are like essentially cosines spinning around the sphere. And these are second order terms. And what Ramamurthy and Hanrahan showed is that fairly complex lighting can be estimated as linear combinations of the first 9 spherical harmonics. These are functions on a sphere, and you can model them. So if you have, for example, very strong directional lighting, you'll need some of these, but these are sort of the second order terms that deal with some of the more complex interactions. Okay. And I won't go into the details of how we do this, but we can take an image, and with a couple of tricks, we can now estimate complex lighting environments that go beyond just where is the direction of the light source. So in this case, for example, if we do sort of the same analysis we did for Brad Pitt and Angelina Jolie, it looks about right. This guy is brighter here than here, brighter here than here, brighter here than here. Looks like it's about ballpark. It's not 120 degrees differential. But if we estimate the light environment, and then what we can do is we can render spheres with the light environment they were under, you can see that these two guys have the light that's coming more from above, and this guy over here, the football coach, is coming in from the right. So it's about 15 degrees or so differential, and we can actually measure these with fairly fine granularity now. Okay. So I promised you I'd show you how you can get 3D light direction, so let me do that next. I don't have a watch, and I don't see a clock. Oh. How embarrassing. Now I don't know when I started. Is it 10:30? Okay, so I have 15 minutes, right? Okay. So this photograph was sent to me by the director of photography at the AP Wire, who occasionally sends me photographs he's about to run and is a little worried about. And this one was bugging him. He wasn't really sure why. And we started sort of poking around. And at first, something about it bugged us too. The first thing I noticed is that this guy seems to be illuminated from the front. You see the hot spot on his head. But this guy seems to have lighting coming in from the sides over here. So something about the lighting just seemed a little quirky. I wasn't really sure. And the nice thing about AP is they have really high resolution images, and so this came at high res. And what I'm showing you along the top here is a magnified view of each of the person's eyes. You see it? Yeah. It's cool, isn't it? So what's happening? Those little white dots, what are they? They're a reflection of the light in the room. So the eyes are great. So what you see is this guy here and the woman here. They have two little dots, which is pretty standard studio lighting, two diffuse light sources set off. By the way, it's consistent with the here. You notice, by the way, she's got a ton of makeup on. That's why you don't see any lighting going on with her, which is pretty. So it's actually a really interesting thing. When you have photographs of a man and woman together, it often looks like the lighting is completely wrong. It's all makeup. Now, he usually has makeup on, but apparently, I don't know what happened that day. But this guy has a diffuse light that's maybe off to the left a little bit, and this guy was taken almost certainly with a flash, which would explain the hot spot on his forehead. So these little specularities in the eye are really, really fascinating. And by the way, once I started noticing these, I can't watch television anymore, because every time they do a close-up of somebody, you see the white dots, and you start trying to figure out where the lighting was, and it totally screws you up. And I hope it screws you up, too, because it makes me crazy. You should appreciate that. What I particularly like is the images of people in caves, and then you've got like these really nice diffuse lights on their eyes. Okay, so here's you don't need any math, right? Just if you have images of people, you can look at those little specularities, and you can see whether the size of them is roughly consistent. We also know that the color right at the center tells you about the color of the light. So if it's a little reddish, a little greenish, a little whatever, you can actually tell that by looking at the color. But what we were particularly interested in is, can you use this to tell me where the light was? Okay? So why would we do that? Well, we have techniques for telling you where the light was, but only 2D. The thing about the eye that's really cool is it's essentially a sphere. And that means if it's roughly a sphere, that means you have 3D surface normals. And that is actually really cool. Well, so it turns out it's not really a sphere. It's a little bit more complicated, but I'm going to get that in a second. But let's first do the basic imaging. So let's assume we have a perfect reflector, the eye. We have a light source over here pointing in the blue. We have a surface normal at the point of the specularity, and we have a camera. So what we know from basic physics is that if the angle of incidence equals the angle of reflection, so that is when the camera is equal to theta r, where theta r is equal to theta I, then you will see the specularity. That's for a perfect reflector. Okay? So you can take this basic geometry here, and you now have a relationship between the direction to the light source, that's what we care about, the surface normal, hopefully we're going to be able to do that, and where the camera is relative to the specularity. Do a little bit of geometry, and you get a very simple relationship between the light direction and the view direction of the surface normal. So if you can get surface normals, 3D, and you can get view direction, 3D, game's over. I can tell you where the light is in 3 space now. Okay, so the hard thing is the 3D surface normal. Well, so the good news is some clever ophthalmologists have gone out and made some pretty careful measurements of human eyes. And it turns out we're all about the same. You can model the human eye as 2 spheres. I'm showing a cross-section of it here. There's a big light gray sphere and a darker small sphere. They are offset by a distance d, the centers, and they have radii r1 and r2, respectively. And that turns out to be a pretty good model for the human eye. You can see the actual human eye here. And they've made measurements from lots and lots of adults without any type of degenerative disease. And they found that the measurements for the radii and the diameter are what I show here, 11.5, 7.8, and 4.7. Women are about 0.1 millimeters smaller than men in terms of the eyes, but well within the realm of what we need for resolution. So we now have pretty good 3D models of the human eye. It's a sphere. And if you know it's a sphere, you've got the surface normals. That's the best possible model you can have. So when we did this is also the work of Kimo Johnson, we thought, all right, a month, the whole thing's going to be over. We're going to have this thing wrapped up, and we'll write the paper. And we started working on it and realized we had a real problem. So the problem is this. Remember I told you that to get the light direction, I need the view direction and I need the surface normal. But the problem is, we have them, but they're in the wrong coordinate systems. The surface normal is with respect to the eye, the thing in the world. But the view direction is the point from the camera out to the specularity. Different coordinate systems. This is camera coordinates. This is world coordinates. I have to take algebraic combinations of those vectors. I can't have them in different coordinate systems. So all of a sudden, we had a camera calibration problem, which is like a nightmare. So we spent a lot of time trying to figure out how to do this. And it turns out you need both eyes to make this work. So if you consider the fact that the limbus, where the dark meets the light on your eye, is roughly a circle, which we know because the model is two embedded spheres, and if you assume that the eyes lie in a common plane, then you have two circles on a plane. And we know from projective geometries that if you have two circles on a plane, I can tell you the transformation from those two circles to the camera. There is a simple homography. It's not a full-blown camera calibration that you have to do. You only have to determine the planar homography between the camera and the world. And that can be written as an intrinsic matrix, which embodies focal length, and the rigid body transformation, R1 and R2, are the first two columns of the rotation matrix. T is the translation vector. And the good news is estimating planar homographies is actually much, much easier than full-blown camera calibration, and you can actually do this, leveraging some nice work from projective geometry. I'm going to skip over the details of this. If you're interested in it, you can dig up the paper on our webpage. The basic idea is that we can simultaneously estimate the parameters of the models and the homography, and we can get the surface normal and the view direction in the same coordinate systems, and you now have all the pieces that you need. So in this slightly creepy simulation, we created a CG world. We had a camera. The camera always had a light source in the yellow vector here. That was one light source, and then a second light source in one of these four positions. The eyes were placed in one of four positions here, and then moved forward and backward to the camera, so we had different resolutions. And of course, in the CG world, we have perfect everything. We know all the things we need to know. What I'm showing you here are just a sample of the data we collected. Here is the limbus. From the two eyes, that's the green dotted line. The little red dots denote the specularities. That's the reflection of the two light sources that I told you about. In general, we're able to estimate 3D light direction within 3 degrees. Standard deviation is 1.5 degrees, and the worst error was 7 degrees. And interestingly enough, these don't have to be super high resolution. The eyes were about 50 by 50 pixels in the image. So you don't need, for the person to take over a full 6-megapixel image. You can do this at relatively coarse resolution, and you're down at about 3 degrees in 3 space, by the way. That's 3 degrees in 3D. Now, for real images, Kimo wasn't quite as clever. He couldn't figure out a way of putting a sundial somewhere that make this happen. Plus, we had to estimate in 3 space. So what we did instead was we downloaded a whole bunch of images from Flickr. That's what I'm showing you here, a subset of them. And in each of these people, you could see specularities in the eyes. And what we simply tried to do was determine internal consistency. We don't know where the actual light was, so we just asked for each person in each image, estimate where the light is, and tell me what the internal consistency is. We're assuming these are authentic, obviously. So in this case, we're within about 6 degrees. The worst case was about 13 degrees. So let's call it 15 degrees in 3 space. So you got a pretty tight cone that you can actually estimate 3D light direction to from, obviously, just the eyes. Or any specular surface where you happen to have a 3D model. OK. So I started off by talking about the issues of digital tampering. We are seeing it in the media. We are seeing it in science. We are seeing it in law. We are seeing it in national security. And we're seeing it everywhere. Every day, 7 days a week. This issue is hitting us, and it's hitting us hard. And so my lab at Dartmouth for the last 10 years has been thinking about computational techniques for authenticating images. And I spent a lot of time talking about image forensics. I've highlighted just a few of the things that we've done. We've developed now close to 24 distinct tools, each of them going after specific forms of tampering. It's important to say that there are, I'll get to that point here actually in a second. Wei-Hong Wang in my lab is doing some nice work in video forensics, so trying to take all of this and dealing with video. And we have a sort of starting in fits and bursts efforts in audio forensics, although there's still a lot of work to be done there. And Eric Key in my lab, a new grad student, is doing some interesting work in document forensics, so printed documents. So thinking about laser printers, inkjet printers, scanners, things of that sort, obviously very different type of statistics than you have with images. So it's important when you talk about forensics to start thinking about countermeasures. Every technique that I've described can be circumvented. And the way I think about forensics is the way the Secret Service probably thinks about currency. They keep adding new technology into currency to make it harder and harder and harder for counterfeiters to make money. They are aware that they do not make it impossible. What they do is they make it painful. They make it time-consuming and expensive. They take it out of the hands of the amateur, and they make it more and more and more difficult. And that's essentially what we are going to do in the forensics game. We are going to make it more difficult for people to create forgeries. We will never, ever win this game. It's the spam and anti-spam and virus and antivirus. You just keep raising the bar. They keep getting smarter. You keep raising the bar, and the game keeps going on. I think that we are getting to the point where it is hard for an amateur to create a convincing forgery. It takes a fair amount of skill these days if you take the full suite of tools that we have. Since I'm here at NIST, we should talk about standards. One of the places where I see a lot of issues, two huge issues with authentication, is the media and the law. And those are both really interesting because I think, unlike the wild, wild west of the internet where you really do need these passive techniques, I think the media and the law can actually do something much more concrete. They can, for example, and this gets back to what I started talking about earlier, insist that we have some type of secure camera where there's a digital signature extracted, a digital watermark inserted. So if you are, for example, a law enforcement agency and you are photographing a crime scene and you don't want somebody later on down the line to claim that you doctored the photograph, or if you are a photographer and you work for Reuters, or you're a freelance photographer and you don't want somebody accusing you of doctoring photographs, I think that there are things that law enforcement, the media, camera manufacturers can do to establish a standard for signatures, watermarks, secure hardware, so that if you are lucky enough to have that type of camera, which in the world of law and media you do, I think you can start to say something very powerful about whether images, video, audio recordings are authentic. So I think there is a place for NIST to start interacting and start making proposals for how we can actually do this. I can tell you that Reuters, the AP, are very, very interested in this, and law enforcement is kicking and dragging a little bit, but they're going to have to get there pretty soon. And I think with that, I'll stop. Thank you, and I'm happy to take questions.